Phi was then 90 degrees, so they always repel each other. Today I want to do a more controlled demonstration whereby I can actually calculate the self-inductance, and I also can calculate the resistance. And what I will do today is I will have a coil which is stationary, and I will have a conductor which is not stationary. Here is my coil, AC, 60 Hertz. There's the coil. And I have a ring, and the ring is made of aluminum. And I know exactly the dimensions of this ring. I know the radius, it's about 5 centimeters. I know the thickness, I know everything. It's an aluminum ring. And has a radius of about 5 centimeters. Since I know all the dimensions, I can calculate the resistance of that ring. You should be able to do that too if I gave you the dimensions. And so the resistance of that ring, very roughly, is about 7 times 10 to the minus 5 ohms. It's very small. That is at room temperature, by the way. At the lower temperature, the resistance is lower. I can also calculate very roughly what the self-inductance is of that ring. Now, that's not so easy. Because here, when I calculated the self-inductance, the magnetic field was constant. I assumed it was constant, uniform inside. That's not the case when you have a ring. You have a dipole field. However, I just assumed that the magnetic field was the same everywhere at the surface of the ring. And with that assumption, admittedly I could be off maybe by 20 or 30%, with that assumption I find that the self-inductance is 10 to the minus 7 Henry. I know what omega is 360 roughly. And so I find that omega L over R for this ring is about 1/2, run at that frequency omega. And that gives me a phase angle phi of 25 degrees. And therefore, the ring is going to be repelled by the coil, and of course the coil is going to be repelled by the ring. I'll put the ring here, and the ring is supported by this, so this ring cannot fall over. The only difference between this experiment and that one is, first of all, I can be very quantitative there. I can actually calculate the phase angle, where here that's almost impossible. Here, it is the conductor that I'm going to make levitate, and the coil is stationary. And here, it was the conductor that was stationary, and the coil is floating. But of course, the idea is exactly the same. And so, what I want to do now is make you see it there, actually. And we'll have to it should come up there. Yeah, there you see this ring. Maybe I should first show you the whole setup. So this ring goes over here. This is an aluminum ring. And I'm going to make it levitate by simply running 60 Hertz, 110 volts through this coil. I hope I do nothing wrong. Oh no, I have to turn on my AC. Oh my God, that was not my intention. A good thing that we don't have a woman sitting on the ring now. My idea was to have it levitate. By the way, you did see that it was repelled. That was quite clear. I had the current too high. So we'll have it a little lower. And I will make the current come up very slowly. And then I want you to see that it levitates. There it is. Levitating. Oh, it's off the screen. There it is. And I can turn it over. And it's still levitating, of course. And the secret is this phase delay introduced by the self-inductance. I have another ring here which has a slot. Also aluminum. Same ring, but it has a slot. Well, the EMF in this ring is going to be identical. There's no difference. In fact, the self-inductance of this ring is identical. But the resistance of this ring is huge, because there's a slot in there. The resistance is almost infinitely high. And so if the resistance is infinitely high, no matter what L is and what omega is, phi is going to be 0. Won't repel. Half the time it attracts, half the time it repels. That means nothing happens. No magnetic levitation. Same EMF, same self-inductance, but an infinite resistance And here you see magnetic levitation. Since the induced current in the ring is extremely small because of its very high resistance, the force on the ring, whether it's repelling or attracting, in any case is